Okay, so welcome to the Tutte Colloquia this week. We are very happy to have Liana Yepremyan talking today. So Liana is now a research fellow at London School, London School of Economy, and she did PhD in McGill, and also afterwards a few years of postdoc in Oxford University. So Liana works on extremal and probabilistic graph theory, and today she's going to talk about size Ramsey numbers of graphs and hypergraphs. So take it away, Liana.
Thanks a lot for these invitations and for the chance. It's a pleasure. It's 11:30 here, so if sometimes you feel like I'm following, I'm a bit slow, please do ask me questions and stop me during the talk. Okay, so I'm going to talk about joint result with some joint work with Shoham Lester and Alexei Pokrovsky, who are both at UCL, University of College London. Okay. So I'm sure that all of you have seen this definition many times, the definition of classical Ramsey numbers for two graphs or two hypergraphs, are uniform hypergraphs, G and H. We say G is H Ramsey, and we denote it by G arrows H if in every two coloring of the edge set of G, there exists a monochromatic copy of H. One of the first examples in any combinatorics course we see is that K5 is not Ramsey for K3 because you can find an edge coloring of the complete graph on 5 vertices with 2 colors such that there's no monochromatic triangle, and I have drawn the picture here. However, one can show that K6 is Ramsey for K3. Okay, so today I'm not going to talk about Ramsey numbers, but the classical Ramsey theorem says that for any fixed t, there exists a big N such that the complete graph on n vertices is Ramsey for kt. So kt is a small clique, and you can always find a big n such that kn is kt Ramsey, meaning that any two coloring of the edges of the complete graph kn, you can find a monochromatic clique kt. Okay, so one can define the Ramsey number RT as follows. That's how it's defined. It's the minimum n among all such n's, such that kn is Ramsey for kt. This is how Ramsey numbers are defined. And there's a lot of research around the Ramsey numbers, and many central open problems in extremal combinatorics are around these numbers actually. Without going into further details, let me just tell you that for any t, there's, I'm ignoring some terms here which are suboptimal, but this is the general bound we have. So RT is at least 2 to the t over 2, and it's at most 2 to the 2t. So you see there's a huge gap here, and a lot of research is around determining, getting closer to determining the right bound. However, so to talk about size Ramsey numbers, first let me talk generally about Ramsey number of any graph H. So for any graph H, the Ramsey number of H can be defined as the minimum n such that the complete graph Kn is Ramsey for H. That is the minimum n such that any two coloring of the edges of the complete graph contains a monochromatic copy of H. We can also equivalently define it as, instead of taking the complete graph Kn here, I can take G, so any G, and I want to minimize the number of vertices in G. So I won't go into details, but these two are actually equivalent. You can define it like this as well. Okay. And the reason why I do it like that, because I want to draw the analog between the Ramsey numbers and the size Ramsey numbers, the main topic of my talk today. So the size Ramsey number of any graph H was defined by Erdős, Fodry, Rousseau, and Schelp in 70s. And they defined it to be the minimum over all G, the number of edges in G, such that G is Ramsey for H. So the difference between this and the classical Ramsey number is that here I'm minimizing the number of edges of the graph, while previously I was minimizing the number of vertices of the graph G. So what's easy to see? Some bounds. First of all, it's easy to see that size Ramsey number is at most the classical Ramsey number, choose 2. Why is that? Well, because if I take the complete graph K on RH, meaning, so this was the classic Ramsey number on the complete graph on RH many vertices, then of course it's going to be Ramsey for H, right? So in particular, the number of edges of this graph is RH choose 2. So this is an upper bound, and in fact this bound is tight, and it was proven by Chvatal, and it's tight for H being the clique KT. Okay, so so we have this bound, and what people of course have tried to do is that they have tried to understand what is the size Ramsey numbers of different graphs. One of the first examples that has been extensively studied was the path on n vertices. So Pn is the path on n vertices, and one of the earliest questions in the area was posed by Erdős, Fodry, Rousseau, and Schelp in their original paper, who asked whether the size Ramsey number of Pn is sub quadratic or not. And then later Erdős asked actually whether, he asked stronger questions. He asked whether it is overlinear or sub-quadratic. This was proved by Beck, who proved that the size Ramsey number is actually linear. It's at most some constant times n. And the host graph of, when I say host graph, I mean the graph which is Ramsey for the path Pn. That's what I mean by saying host graph, is the random graph, GMP, with appropriate H density. So the number of vertices of the GMP we take is some constant times n, where n is the length of the path. And the probability P we take is B over n for some B constant as well. Later, afterwards, Alon and Chuk showed that there are actually other explicit there are other constructions, and they showed actually an explicit construction of the host graph with linear many edges, which was Ramsey for Pn. And afterwards, the research has been mostly around improving the constant in this term ON. So Beck proved that it was at most 900 n. There was the best bound the best upper bound is by Dudek and Pralat from 2017. The constant is 74, and the best upper bound is 3.75 plus little of 1 times n by Bal and De Biaso. Okay, so this is about the path. What about trees? That seems like the natural next thing one would consider. And indeed, this was a question raised by Beck in '83, who asked, what if you have a tree on n vertices and you know that maximum degree is d? Is it true that the size Ramsey number of bounded degree trees is also linear? So it's quite important here that we request that the tree has bounded degree. An exercise could be, if one looks at the star, double star. So what is this? So this, I have two vertices which are adjacent by an edge, and both of them have n many leaves hanging from them. So this graph is a tree. It has unbounded degree, and one can show that, let me call this dsn, the size Ramsey number of double star is quadratic. It's omega n squared. Okay, so indeed the bounded degree here is important. So it's essential requirement. Okay, so let T and D denote the family of all trees on n vertices and of maximum degree D. So today I'm going to use this T and D quite a lot. So remember that. And celebrated paper by Friedman and Pippinger from '80s showed that Beck's conjecture was true. That indeed, if you look at any tree with bounded maximum degree, its size Ramsey number is linear. This paper is very beautiful, and it's very important, I think, in the development of size Ramsey numbers. Okay, so in fact, the proof of Friedman and Pippinger shows that so their host graph is also the random graph GMP with appropriate density. And the host graph is universal, meaning that it does not just contain one tree of bounded maximum degree, it contains all the trees of maximum degree at most D and on n many vertices. Okay. And a question by Beck, also raised by Beck, says, okay, what if now I have any graph G and it has n vertices and maximum degree is bounded? Is it true that then I can imply that the size Ramsey number is linear? So basically, his question was whether the maximum degree is the only thing we need to require to have a linear size Ramsey number. And the answer, so why, first of all, this is a reasonable thing to think about. Why would we, why this is something that we might have expected to be true. So a theorem by Quattal, Rodel, and Samaredi and Trotter from '80s shows that for such graphs G, the normal Ramsey number is actually linear. So we already know that the size Ramsey number for such graphs is at most of order n square. So now it's about determining whether it's between linear or quadratic. But this was actually proven not to be the case by Rodel and Samaredi. Quite late, actually, in 2000, they showed that there exists a family of graphs such that they actually have maximum degree at most 3. And their size Ramsey number is not linear. It's n times some power of log n. This result has not yet been improved, meaning that this is the only construction we know of graphs which have bounded maximum degree and not linear size Ramsey number. So it's actually interesting to come up with, to try to find other families of such graphs. Okay, right. So a conjecture actually by Rodel and Samareti, who I think it's in the same paper that they proved this result, says that one can show that for any D, if you look at all the graphs H, which have n vertices and their maximum degree is bounded by D, then among all such graphs, the size Ramsey numbers are bounded between some n to the 2 minus epsilon and n to the 1 plus epsilon. So basically, they are saying that this polylogarithmic error term actually can be improved. It can be improved up to n to the epsilon. As I said, there is no improvement at all on this result. So we're very far from knowing whether this lower bound is true. But the upper bound, that it is actually bounded away from n squared, was proved by Colloquia, Rodel, Schacht, and Samareti in 2011. Okay, right. So now let me go to other families of graphs, and I'll talk about cycles. So this is the next family that has been studied. And in 1995, it was proven by Haxel, Colloquia, Ruchak that the size Ramsey number of cycles is also linear. So in all these cases, actually, the host graph is the random graph with appropriate density. And the density is constant. So the number of vertices is some big constant times n, and p is some constant b over n. And then there was, for a while, there was not much research around the size Ramsey numbers. Then David Conlon asked the following question. He asked, okay, what about if we take powers of paths? So you fix k and you ask what's the size Ramsey number of kth power of Pn. He asked whether that's linear. So first of all, let me just remind you what is a kth power of a graph G. So it's a graph on the same vertex set as G. And now we have UV being an edge in the kth power if and only if their distance is at most k, meaning that their distance in G is at most k. This was proven by Clemens, Jensen, Colloquia, Morrison, Mota, Redding, and Roberts that this is indeed the case, that the size Ramsey number of powers of paths is also linear. Okay, and then, right, so I should also mention that they also proved that, not the same set of people, actually. I think some people have left the project. But Hahn, Jensen, Colloquia, Morrison, Mota, and Roberts showed that the same is true if you take the S-color size Ramsey number. So I haven't defined what is the S-color size Ramsey number, but you can probably guess is the same as before, except now we are not looking at two edge coloring, but we are looking at edge coloring when we use as many colors. So the S-color size Ramsey number of a graph H is defined to be the minimum. You take all the graphs G and you color them with the edge set by S colors, and you want to find a monochromatic copy of H. And among all such graphs, I want to minimize the number of edges of G. Okay. So what's known about the S-color size Ramsey numbers of graphs, in particular of paths? So in this original paper of Beck from 83s, it actually one can deduce that also the size Ramsey number, the S-color size Ramsey number of Pn is linear. The proof is not explicit, but it can actually be derived from S equals 2Ks. What's known about paths in general for any S, so the best lower bound that's known is by Dudek and Pralat, who showed that the size Ramsey number, the S-color size Ramsey number of Pn is omega S square n. And the upper bound is by Krivelevich, who proved that the upper bound, an upper bound of s squared log Sn holds. And the question is which one is true, and I think it is much more believed that the lower bound is the true bound. So basically it's for S-color size Ramsey number of the paths. Now it's about understanding what is the right constant in terms of S, just the order of S. Okay. Okay, so I started working on this problem with Nina Kamchev, Anita Libanau, and David Wood. I was visiting Monash University and University of Sydney. So we considered the problem of powers of trees. So recall that T and D denotes the family of all trees on n vertices and of maximum degree D. What we showed is that generalization of the result that I previously mentioned on paths. So if you take, there's a typo here. It should be K here. So without K, this was already known by the result of Friedman and Pippinger. And what we proved is that if you take any tree of maximum bounded degree and you take any Kth power, then its size Ramsey number is linear. Independently from our work, Berger, Koakava, Maesaka, Martins, Mendonça, Moda, and Parchuk showed that the same result, plus they showed that also the S-color size Ramsey number result holds, meaning that for all such trees, I don't know why I have this typo here. So there should be power here. All trees, all K power of bounded maximum degree trees have a linear size Ramsey number for any color S, at least 2. Okay. And the last family of graphs that I would like to discuss is the size Ramsey number of subdivisions. So what's a subdivision? The Q subdivision of a graph H, which I will denote by HQ plus, is obtained from H by replacing every edge of H by a path of length Q. So if, for example, I have K3, then it's, I don't know, let's say K3 subdivision 3 plus would be same graph, except now I add some new vertices inside such that I obtain a path of length 3. Okay, so the size Ramsey number of such subdivisions have been also studied. And the most recent result in this on these graphs is by Dragonich, Kribelevich, and Nanadov, who proved that if you have a graph H whose maximum degree is bounded, then if you take any size from any subdivision is going to be bounded by some constant times n to the 1 plus 1 over q. So you can see that the more you sparsify your graph, meaning that the larger subdivision you take, as q goes to infinity, this number becomes closer and closer to being linear. What they also showed is that if q is at least some constant times log n, then the size Ramsey number is linear. Okay. So the first result improves some results on Koakava, Retter, Rodel. And the second one actually solves a conjecture of Pak from 2002. So this is related to some computer science problem. Okay. Now, our recent work mostly comes from the perspective of hypergraphs. So before starting our work, there was a paper by by Dudek, Thormu, Bai, and Rodel from 2017, where they considered size Ramsey numbers of hypergraphs. And one of the first graphs that they considered was the graph P and R. So that's the R uniform hypergraph, R uniform tight path on n vertices. So you have n vertices, and every consecutive R vertices are in an edge. So your verses are put in order. And for example, if I'm, so this is, I have P6, and if I'm looking at tree uniformity, then I make every consecutive triple to be an edge. Okay, so they raised the question whether the size Ramsey number of the tight path P and R is linear or not, and what they proved some upper bounds, and the best general result, which was known prior to our work, was that the size Ramsey number of P and R is, so this is just a constant, so basically n times log n to the R over 2. For R equals 3, it was proven that it is linear. So the size Ramsey number of a tight tree uniform path is linear. This was done by Han, Koagawa, Lester, Moda, and Parchuk. What we did show is that their question holds. The size Ramsey number of our uniform tight path is actually linear. In fact, much more is true. We can also take any fixed power of such path, and the size Ramsey number of such hypergraphs would also be linear. Right, so what is so I haven't defined for you what's a Kate power of a path, but okay, so for any K and any R, any N, if I'm taking all the R subsets of any R plus K minus 1 consecutive vertices. For example, if R was 3, then let's say I'm taking any 4 many consecutive vertices.
Liana?
Here I must.
Liana, I think your screen is not shared anymore.
Oh, really?
For some reason.
Okay. Has this been for a long time?
No, just now.
Okay. One second. Yeah, I see my iPad is struggling to connect. I think it's an internet issue. Let me try something else. Yeah, okay. Okay, so can you see it now?
No, I don't think it is in the, you try to log in from the iPad, is that right?
Yeah.
It's not in the list. It's not in my list of participants, so I cannot see your iPad here. Maybe you could try, like Zoom has a function of connect to your iPad using either Wi-Fi or using a cable. Have you ever tried that?
Yeah, usually it's a problem to do it with my cable. 1 second, I'm reconnecting to it again. Okay, so it seems like I'm connected now. Okay, can you see it now?
Yeah, that's right.
Okay, Okay. Okay, so I was talking about Kate powers of tight R uniform paths. Okay, so the definition of it is that you put your n many vertices on the line, and every R plus k minus 1 consecutive vertices must make a complete graph. So if it was, for example, for R equals 3 and k equals 2, for any 4 vertices, I would have to put a complete 3 uniform graph. So all the possible triples. And I think the last one, which one I'm missing? I think it's this one together with this. So this is how we define the Kate power of our uniform paths. And we show that the size Ramsey number of these graphs is also linear. Right. In general, we actually proved that also the size Ramsey number of hypergraph trees is linear. And the way you can define hypergraph trees, I mean, you can define it in various ways. We are using the definition that Dudek et al. Have used. So an R uniform tree is an R uniform graph with, so edges are ordered, E1, E2 up to EM, such that for all I, EI intersects the union of all the previous edges in some set, which is a subset of some EI0, which comes before I. So if you think about it, just the normal graph trees are also satisfy this definition, because you can just call this one as E1, this one is E2, E3, E4, so on. And you can see that if you just order the graph like this, then it does satisfy this definition. The point is that the I is in a set which is included in some edge that appears before I. Okay, so what we prove is that if you take an R uniform tree on n vertices and the maximum degree is bounded, its size Ramsey number is also linear. So here it's also important that you take the maximum degree to be bounded, because this example that Rodel and Samradi had for graphs can be also generalized to hypergraphs, and it was generalized by Dudek et al. Indeed, we must have maximum degree to be bounded. Okay, yeah, and we also proved that the same result holds if you take Kate power of such trees. And again, you can define Kate power of trees in various ways, but we just use the analog version from the paths. So we define it to be as follows. For any R uniform graph H, its Kate power is defined to be on the same vertex set as H, and now an R tuple U1, U2, UR is an edge in H to the K if it's contained in some tight path on at most R plus K minus 1 vertices in H. Okay. Finally, all of these results that I mentioned, I kind of show you a build-up, so powers of paths, powers of trees, but they actually come from a more general result. However, before going there, let me just say that if I define for graph G, KRJ to be the R uniform hypergraph on VG, whose edges are the R cliques of G, so you can think about this, so you take the graph G and you make a hypergraph out of it by taking the R cliques to be edges. Then what we show is that if you take any tree T, which is of maximum degree D, so bounded maximum degree, and you take all the R cliques of such a graph, the strongest result among all the previously mentioned results for the powers of paths and powers of trees. One can show that the way I defined powers of hypergraph trees or powers of paths will be a subset of such definition. So if I just take any bounded degree tree and take its kth power and then take all the arc cliques of such a graph. Okay, and finally, I should mention our results on powers of hypergraph subdivisions. So, so I defined Q subdivisions of graphs. And what was it? It was obtained from H by replacing every edge of H by a path of length Q. For subdivisions, what we prove is that if H is a graph on n vertices and of maximum degree D, and Q is at least logarithmic in n, then if I take the Q subdivision of H and I take its kth power, and then I take all the arc cliques of this graph and think about them as edges in a hypergraph, then such a hypergraph also has size, linear size Ramsey number. Okay, so as I said, in general, our proof is in a more general setting, and we prove it for a family of graphs which can be obtained by the following operations. So ANDL will be the family of all graphs on n vertices with maximum degree D that can be obtained from a single vertex by doing one of these two operations. The first one is if I have the graph gi minus 1, what I do is I just add a leaf to it. And the second operation is that if I have gi minus 1, then I take two vertices of it and I add a path where I add L new vertices to make this path. And the general result that we prove is the following, that if you take any graph in this family and you take its kth power, and then you take the graph of arc cliques, its size Ramsey number is going to be linear. It's not hard to see that all these previous mentioned families, the hypergraphs of paths, trees, are all they can all be obtained as part of this family. Okay, so now that I have mentioned our results, I want to, in the remaining 20 minutes, I want to try to give some glimpse of proof ideas. Okay, so let's first go a little bit back to how previous proofs for, say, graphs worked. So R equals 2. So suppose we would like to show that the size Ramsey number of powers of paths, just the normal graph paths, is linear. In this case, the host graph is a complete blow up of some power of a bounded degree expander graph. Okay, I mentioned a few things here, so I need to explain to you what is, first of all, what do I mean by saying H is an expander? So I will say that it's an expander if for any two sets, A and B in H, such that the size of A and the size of B is linear in terms of the number of vertices of BH, there's always an edge that goes from A to B. This is what I mean by H being an expander. In fact, H can be taken to be GMP with the random graph with appropriate edge density. What's important is that we require that H is of bounded maximum degree, meaning constant maximum degree. So what you can do to obtain such an expander, you can take GMP with, so you can take H to be, sorry, can take H to be G and P, for N being some large constant times N, and P being some constant over N. And then you can clean up all large vertices of large degree vertices, and the remainder you can show that will satisfy these properties. Okay, the other thing I need to define is this operation FKQ, which is the complete blow up of a graph F. What I mean by this is that if I take, if I have two vertices UV, so any vertices, I replace the vertices by a clique of size Q. And I'm gonna call this the blob for U, and this is the blob for V. So these are two cliques on K vertices. And if UV have an edge in the original graph F, then in F to the FKQ in the blow up, I have a complete bipartite graph going between these two blobs. Okay, so for the power of paths, our host graph is going to be, we take some expander, we take some kth power of it, and then we blow it up by some large cliques. Okay, so let's see why such a graph would be a host for PNK. Well, first of all, so given any two coloring of the edge set of G, what I would like so I want to find a monochromatic copy of PNK. What I know is that by Ramsey's theorem, right? If I'm looking at all these blobs, which are in HK to the KQ, the edges are colored red or blue. By Ramsey's theorem, if my blobs are large enough, some of them are, I'm going to be able to find large cliques, monochromatic cliques inside them. Some of them will be blue and some of them will be red. And I will just take the majority of such, so I will take the majority color. So if blue is the most common color that I see among this blobs, then I discard everything else and I just look at the blobs which are blue. So so I discard these guys and I just look at, I just zoom in only into the blue sublobes. Okay. So then we can define an auxiliary coloring of the complete graph Km, where M is the number of blue sublobes. So all I'm left with now is just blue sublobes. Okay, so they're still large, like some KT. And I know that M, the number of such sublobes, is at least B of H over 2. And now I define the following auxiliary coloring. I look at any, so for each of these blobs, so this is some blob PU, PV, this vertex U and V come from H. And I say, okay, if there exists a large blue complete bipartite graph here that goes between the blobs, then I color this edge to be blue. Okay, this is this case. Otherwise, I color it by a red color. So if there is no such large blue complete bipartite graph, I'm going to color the edge UV by color red. Here, you might wonder about something. You might say, okay, but there might just be no edge between U and V in H, which is okay. I'm still going to color it by red. And I'm going to remember this. This auxiliary coloring idea goes back to Peter Allen, Brightwell, and Joseph Skokan. And the main lemma that's used using this auxiliary coloring is the following. Either the complete graph Km is going to contain, after this coloring, either you are going to find a long blue path, okay, what would it mean if we find a long blue path? It would literally just mean that we can basically find our path the way we want it. Because if there is a large KSS going between the blobs, okay, so they might not go to exactly the places we wanted, but because everything inside these subblobs are blue, we will be able to find our large power of a path. Or in the other case, when so either you will find such a long blue path, or you can find a large red complete multipartite graph. What do I mean by this? I mean, you are going to be able to find many so large sets, VIs, such that all the edges in between are red, and so on. And these guys are going to be of large size. They're going to be of size omega n. In the second case, what we do is we try to obtain a red embedding of the path. Okay, so without going into further details, let me just say that if the number of colors becomes more than 2, this becomes much more ad hoc and much more technical, because you if you don't find, say, a path in one color, then you no longer can say that, okay, I'm going to find a red large multipartite graph in the other color. You'll find it, you will have many options. It is no longer going to be just red. So one of the new ideas that we have brought into the picture is the following. So our host graph is going to be the following. It's going to be, we'll still take some H expander, and we'll take some Kate power of it and a Q blow up of it. And then we'll take the R cliques of this graph. One of the first lemmas that we prove is that in any S coloring of such a graph G, you can make sure that the edges of the same type have the same color. So now think about this not as just graphs, but any R uniform hypergraph. What do I mean by two edges having the same type? Two edges have the same type if they intersect every blob in the same number of vertices. So basically what this means is that if, for example, I'm looking at edges which go, say, through blob U1, U2, U3, intersecting each of these blobs just exactly once. So imagine I'm looking at 3 uniform graphs. So if I have edges that are going like this, intersecting each blob exactly once, then all such edges have to have the same color. And if I look at edges which, for example, intersect U1 twice, the blob of U1 twice, and U3 once, then such edges must have also the same color. So what this immediately already tells you is that you have a lot of structure, and you can think about the vertices inside the blobs behaving the same way. So vertices inside the blobs, you can treat them as the same vertex. The proof of this lemma is by applying Ramsey type results for each edge type. And every time you apply it, the blob shrinks a little bit, but because the original graph H has bounded degree, none of the blobs will shrink too much. And right, so instead of looking for a monochromatic copy of a graph F, now we actually can look for a monochromatic homomorphic copy of the graph H, because I'm gonna treat every vertex inside the same blob in the same way. They are going to behave. Okay, so for example, if I was looking for a monochromatic tight path, now I'm going to look for a monochromatic copy of a tight walk, where every vertex repeats only constant many times. I just don't want to have any vertex to be repeated too many times, because for example, if I was looking at the nth power of a path when R is 2, then my new auxiliary coloring would be as follows. I would color an edge UV in HK by color C if there exists a short C colored nth power of a path starting with L vertices in the sublobe of U and ending with L vertices in the sublobe of V. Otherwise, I'm going to color it gray. So meaning if I'm looking at the sublobe BU and sublobe BV, and I know that there exists some short path that starts here, some L vertices and goes here. Okay, if there exists some short tight path, I'm talking, well, for R at least 3 it's a bit different, but for say uniformity 2, then if there exists such a short path, I'm gonna color the edge UV by color C. And if there is no such path, then I'm gonna color it gray. What happens is that now if I can actually find a monochromatic path that's long, so if I can find something like this, so I have a lot of, so I have a path here and another path here and another path here. Okay, so you can see that the endpoints here are not necessarily the same, but you can actually do some shifting to make these endpoints to be the same and find your desired monochromatic long path or power of a path. And this is the main the main lemma about auxiliary coloring that we prove is that either there exists a monochromatic PN in the auxiliary coloring, or you are going to find many disjoint gray cliques which cover most of the vertices. What this allows us to do is that you either are able to find a long monochromatic path, or if not, what you end up seeing is structures like red blobs and between them, say blue edges, all of them. And then what you do, you iterate this process, and what you end up seeing is things like this, many such things together, and between them you see yet another color. So I see, say, green edges that goes from one such bit to the next one. And what happens is that you have only as many colors, and if you keep repeating this process after as many steps, you are going to have to find a long path. It's very vague what I'm saying, but that's the main idea. Okay, right. And so this was the idea for many colors and R equals 2. For R at least 3, we instead of just looking at these blobs, we associate order trees to every vertex of the graph H. And order tree is basically a tree together with a planar embedding of this tree. These trees help us to have more control of how to embed various hypergraphs. We prove several Ramsey theoretic results about ordered trees. Like, for example, that if you have a large ordered tree, which is has degree D, then for any S coloring of the R sets which leave on of the leaves of this tree T, I will always be able to find some smaller Dairy tree such that edges of the same type, and now type is going to mean something else, but similar to what I explained to you before, when the type meant that two edges were intersecting the same blob in exactly the same number of vertices, such that the R sets corresponding to isomorphic ordered trees have the same color. Anyways, these ordered trees help us to embed to embed the hypergraphs we want for larger uniformities. Unfortunately, I don't have time to go more into detail there. But yeah, let me just mention open problems. So as I said, the Rodel and Semeredi, Rodel and Semeredi had this conjecture that for any D, there exists some epsilon such that if you have a graph H which is has maximum degree D and number of vertices n, then you must be able to find some such graph whose size linear number is going to be n to the 1 plus epsilon. So we do know that this is true if we look at n times some log n to the c. But the question of whether we can improve it to n to the epsilon is wide open. And the second problem I would like to mention is the size Ramsey number of the n by n grid. So what's a grid? You probably have seen a graph like this, and where we have n rows and then columns. It's a question whether the grid has linear size Ramsey number or not. Clemens, Miralaya, Redding, Schacht, and Taras proved that its size Ramsey number is n to the cube plus a little of 1. And here the host graph is the random graph as well. And using random graphs, you cannot go lower than this. I mean, you can improve this little O1 maybe, but not lower than that. And it's wide open whether it's close to linear, meaning n square, not that it has n square many vertices. So linear here means n square, or it's closer to n cube. Okay, that's all. Thank you very much.
Thank you, Linnea, for the nice talk. So let me see if there are any questions from the audience. Maybe I'll start with one. So in your, sorry, I haven't, I did, sorry. So in the earlier slides, you listed those results for the size Ramsey for paths, and I think there has been quite a bit of recent progress in improving the constant coefficient, starting from proving linear bounds, and then there are something like 700 or 14 or something like that. The size Ramsey for paths. Did people try to do similar kind of thing for say cycle or tree bounds for the constant coefficient with n? Do you know if people ever try to do that?
So I don't know. I don't think I'm not sure if for cycles have this constant has been improved or not. I'm not sure, but I think it was for the paths that was mostly done the research. But maybe for cycles there is something which I just haven't paid enough attention.
I see, but the original paper was just like some big of n, and they don't care at all about the constant, or there is some specific constant.
I think that you can derive the constant there as well. I just don't.
I see.
Yeah, I think I mentioned paths mostly because there it's really has become like a central attention, while for cycles, I think it hasn't been studied that much. But yeah, I think from the paper of Haxel and Koyakawa, one can deduce what the constant is.
I see. And also for this last this conjecture that you mentioned in the open problem, is it so this H? Do people know if you take a random graph with bounded maximum degree, let's say, is it known that it is a linear Ramsey bound or it's superlinear? Is that known?
If you take
a random graph, or maybe just take a random regular graph.
I see what you want to do. I don't know the answer to the question, I think. It's a very good question. It's very natural thing to consider, right? Because if you want to understand these conjectures, then I don't know the answer for sure, but if I were to guess, I would be more prone to think that for random regular graph, it would be linear. Rather.
So the construction that they got this n log thing is very special family.
Yeah, it's bunch of trees. So they take binary trees. It's the same tree. Okay, so many of them. The number of such trees that they take is based on linear ordering of. So they put a Hamiltonian cycle that goes along the leaves of the tree, and of course, based on the ordering, you get many such trees. And then at the end, what they do is, I think they add. So I think they add one more vertex like this on the top. If I'm not 100% sure, but then they connect these roots to each other. Something like I forget exactly how the last bit is done, but I think it's something along this line. And the problem, like where the problems arise, meaning that why it's not linear, it's because of this the cycles that they put here. So it's very non-random.
I see. Okay, thank you. Other questions? All right, if not, let's unmute ourselves and give applause to thank Liliana to give a talk in such a late time. Okay, I'm going to stop the recording.